let's roll in on the ominous sign and a few other attendees. Just to introduce myself, I'm Joe Berry, and I've been tinkering around in GIS. If you attend the third lecture in this series, kind of the war story one, I think since 1954. Now that's before we had computers, so I'll have to explain that. But I can really defend since 1967. It was the first digital map that I got involved with. It wasn't until 1976 that we conjured up the acronym GIS. So, been around this for a long time. I approach it differently than most folks. By far, the field treats maps similar to how we handle them manually. Spatial objects. Most of you heard about that. Points, lines, and polygons. Well, that's what we could draw. So that's our mindset of what a map is. It's a collection of your regular points, lines, and polygons, and it all comes together, and you got this kind of rendition of a landscape. My doctorate here at CSU was in remote sensing. And we view the world that way as a bunch of little squares. The problem is, in the early 1970s, the little squares were big things, all over several acres, and blurry. No, it's not a map, it's this blurry little thread thing. But what we did that was different is we treated maps as data. And that'll be kind of the theme here. Maps, rather than being graphical portrayal of the pattern formed by points, lines, and polygons, we're going to treat it as a continuous mathematical, numerical surface. Intention will be, when you buy into all of this, is that there's a true mathematics. Now in math, there's such a thing as matrix algebra, accepted, taught, dealt with. It says you organize numbers in a matrix, and where they position in that matrix means something, but not like we tie it to geography. I'm trying to come up with the idea that's really an extension of matrix algebra. Our matrices are just great big huge things, probably with 4 to 5 million cells. That's a big spreadsheet. But conceptually, it's a spreadsheet. So maps are numbers first from this orientation, pictures later. So that's what we'll play around with. Now, you may get so excited about all this that you're willing to go to what I'll click on in a second. It's in this first slide, and it's in all the handouts. I put together a web page for the Centroid stuff. And if you'll note, every slide is in there, just the way I'm showing it, and instructor notes. So it's kind of like a little tiny textbook tied to this thing. So keep that in mind. If anything titillates you, there's lots of references in there and even discussion. Otherwise, if I do go to that location, it has the handout, it has that PowerPoint, and then it has it for the rest of the series. And it also is my promotional pitch. Some of you got this, it's a handout. I just got through writing a column in GeoWorld for 25 years every month. Finally, it's together as a compilation of about 1,000 pages, 750 graphics, a lot of them are animated, and to get through that horrible pile of information, I put together 5 different indices, ways to get at it, listings to get into it. You can get at it by application type, by operation type, by the functionality, the algorithm, chronologically, and a whole bunch of different ways. That may be a resource you want to tinker with. All right, that's the prelude. Now let's get on with the show. The premise is that there's a mathematics. Mathematics. that extends traditional math and stat concepts and procedures for the quantitative analysis of map variables. Oh, I can see sweat pouring. I can see people looking down at their shoes. Like right there, I said quantitative and I said variables. Oh my God, I'm out of here. I don't know. If you're going to stay with GIS, maps are numbers. You got to do some number things. So let's play around with that idea. I like to think, I have trouble with geomatics as a word to describe this field. I have trouble with geospatial technology. It seems redundant to me. The word I like is geotechnology. That's what this is involved with. And so does the U.S. Department of Labor. And they say there are 3 mega technologies for the 21st century. 3 for the entire century, for the next 100 years. Probably cover your lifetime. There's only 3 mega technologies. Bio, you probably heard about, and the trillions and trillions of dollars that go there. Nanotechnology, CSU's really good in nanotechnology. Little atoms washing your window and stuff like that. And then there's this thing called geotechnology. It's a mega technology, and the definition of a mega technology is it's going to change society. It isn't going to make it easier for us necessarily, but it's actually going to change society and culture. It's the spatial triad that's been around since the last 100 years or so. Remote sensing, aerial photograph, World War I, II, satellites, okay? Global positioning system, military had that. I know. Late 60s, early 70s, came on board for us in the 90s. And then this thing called geographic information systems. And what it does is it maps and analyzes spatial information. GPS locates and navigates. And remote sensing measures and classifies. So if we take this GIS portion, well, there's kind of 2 ways that we approach it. We approach it as a technical tool, technological tool. We're going to map with it. We're going to replace the cartographic process, which in my day, your age, I was dragging little pictograph pens around on acetate sheets to draw maps. Okay, we're going to display them differently. My God, beautiful. Look at graphics, 256,000 shades of color, 3D, animated. Yeah, we're changing what a map display is. And then geoquery. This is your bread and butter. What's here? Whoosh. Allows us to search spatial information. That was difficult beforehand. But then there's another perspective on GIS technology. That other perspective says it's an analytic tool. All spatial mathematics, actually it did with Descartes 280 years ago. Cartesian coordinate system. Boy, there's a lot of math behind jamming around those projections and all that. So there is an adopted spatial mathematics, but it's primarily to flatten out our round Earth. And a few simple analytics. But then this spatial analysis says it investigates the contextual relationships in spatial information. And what I mean by that is if I'm here, and over there is another place, and I'm sitting up in Estes Park, or Rocky Mountain National Park, could I see that other place? Am I directed? Am I connected contextually in geographic space? If I were to walk from here, I probably wouldn't walk in a straight line because I'd fall off a cliff, land in a lake. What would be my route that would connect me? That's a contextual spatial relationship. And that's spatial analysis, which is different than a statistical spatial statistics, a numerical. I'm just going to look at the numbers. Is there a correlation between these 2 maps? Are there significant difference between these 2 maps? And I want to do that statistically, not with a laser pointer, with 2 slides up there visually saying, yeah, sure looks like these 2 things are different. See over here, see over there. We're going to do it statistically, and I'll tell you whether the t-test worked or not. That is a paradigm shift for both mathematics and statistics. And if we're going to pull this off, we're in GIS technology, we're going to have to engage STEM, science, technology, engineering, and math. We aren't going to be able to sit out here in our little enclave, show everyone how to use ArcView, ArcInfo. We're going to have to engage them to think spatially. That's why we're mega technology. We're not a mega technology because we draft maps faster. We're not a mega technology because you can download maps off the internet. Those are pedestrian. We're different because we're going to change science. That is where we want to end up. Spatial statistics, spatial analysis. That's what we'll play around with. Well, Matt Ball, Vector One, has a great blog. And a little while ago, he said there's 3 critical technological frontiers to geotechnology. One was 3D integration. We haven't done a good job with that even today. What that says is there's a bunch of spatial software, if you will, out there, programs. CAD, CAM, BIM, Building Information Management Systems. That's kind of the drafting stuff. Well, they rarely put latitude and longitude on it. We rarely catch the information that they do to their spatial objects. So he's saying that as we go forward, there's going to be a melding into intelligent 3D systems that incorporate not only GIS, but CAD-CAM. It's like CAD-CAM. If you have a CAD drawing of an engine in 3D, you can click on any part and it tracks back. Oh yeah, to get to that, you'd have to take off this bolt, then you have to take off that. All that information about the spatial arrangement and connectivity is part of CAD. We don't do that in GIS. We tell you how big the forest parcel is, and maybe what kind of trees are there. We don't link it to all sorts of things. So that's going to radically change us, and we're going to change them. Then there's the real-time GIS. Excites me a whole lot. And what that's going to do is develop a whole bunch of intelligent machines. See, without GIS, we couldn't fax a map to a machine and have it figure out anything. It had to be in the digital mode. Talk about farming next time, precision agriculture, for example. So real-time GIS has a big place when it comes to the sensor web. A whole bunch of sensors out there, and when you make it nasty, a whole bunch of those video cameras watching you walk across campus. Face recognition programs know it's you even if you put on a fake mustache. All these weird things, but that's a sensor net. Well, that sensor net information is going somewhere, and it's all spatial. It's going to be a pretty critical technological frontier. And then finally, temporal time. So far, we see our environment as X, Y, Z. 3 dimensions. Ooh, there's a 4th dimension, time. And we're wrapping time inside the GIS as a 4th dimension. Well, now those things are really going to change how we, for example, manage our farms. We're going to, with the aid of the computer, come out with all sorts of nifty things and send R2-D2 out there to do some things. We have drones flying around right now, most fields, lots of fields. Weather stations. Now, these aren't just weather stations 50 miles away. I have one client, a vineyard, that has 4 weather stations on his 40-acre vineyard. Kind of into this techie stuff. I'm like, oh, I'll add another one just for fun. But, you know, we can instrument a lot of things. So that's what that's kind of looking at. And we look at it over time and deal with it. And what's really interesting when you deal with maps is data. You can have predictive maps. What would it look like? Markovian transition matrix? And say, well, If you were agriculture and you're a certain distance away from the city and you have a certain amount of water rights, you know you might be urban real quickly. So now let's look 10 years down of what it would look like. There'll be a lot of ag that didn't meet that modeling requirement. So we can model based upon our understanding of space. Actually, look at the future as best we can. Now, how are we going to pull it off? Well, the only way we're going to pull it off is to treat maps as data, not maps as images. Because the human mind can't do this kind of stuff I've been describing. It's just too complex for us. We need a little bean counter, that little tablet PC you carry around, to pull it off. So I'm going to make the next few thoughts looking at what I think are the influences for the future directions of map analysis and modeling. They are this mathematical framework. Let's understand it a bit more. I predict your data structure is going to change radically within your lifetime. 280 years since Descartes, and we're still using the same stupid square. About time to maybe revisit that. And then the educational approach. That's got to change. All right, let's give it a whirl. Mathematical structure. Well, we have this GIS, and as a technical tool, we kind of think of it in the vector world because that's what we could draw. That's where we came from. So we have these discrete spatial objects, your regular spatial objects, for example. Now, when we go into the mathematical world, we're going to treat it as a grid. And a grid, to a mathematician, is a matrix. A matrix, two-dimensional matrix. So you got all these little squares on the ground. Now, originally, that was pretty crummy because it was water. Look at that. One big glob, didn't have to say anything about what's going on inside. It's just assumed. This way, I have to completely describe geographic space. I have to even describe the interiors. My idea wasn't to record a graphical image of objects for human viewing enjoyment. We're trying to turn it in to data. To do that, it has to be continuous. It needs to be in raster. And quantitative best. Real numbers. Because I'm going to take one map, multiply it times another, divide it by a third, and do all sorts of weird things. Maybe take its first derivative. That is a paradigm shift. Make a technology. Got to be something different than just pictures on the screen. Well, this is Esri's spatial analyst. Now it has a toolbox that deals with raster, disaggregated, means continuous, it's not aggregated into clumpy lumpies like a lake, and quantitative, a little bit of qualitative. Well, they have 170 individual tools, and they're organized with things that don't mean squat to STEM people. It means a lot to the programmer that did it. Some of their things in their optimal path routing is under hydraulic tools. Well, that doesn't help them see a comprehensive understanding of this mathematical tool set. So what I propose is that there is a mathematical framework, and let's speak in our client's vernacular. All of these topics you'll see in a mathematics book of books. All of these topics you'll see in a stat book. The contention is everything, those 170 commands, fall into one of those. So all of a sudden we translated it so the scientists can understand this without taking 5 courses in learning how to change projections. Doesn't want to be a GIS specialist. Wants to be a scientist. So they don't come to your courses. If they don't come to your courses, I don't know what the heck space is, and we'll keep working with averages for Larimer County. What's the average birth death per 1,000 women. Well, what does that have to do with Steamboat versus Fort Collins? There's a spatial thing in there, and all of our spatial information gets thrown into something called a standard deviation. We can uncouple it, and we can help, in a very large sense, explain the variation in the standard deviation, and our models should be a whole lot better. They aren't going to dream that up. You're going to have to tell them and show them. All right, let's give it a try. And I'm going to use some nasty, nasty ones here. First, we'll start off easy. Spatial analysis extends a basic set of discrete map features, points, lines, polygons, to map surfaces. That's the first thing. It has to be continuous. Has to be consistent. Has to be the same square. Appears on every map the same way. Not a bunch of irregular polygons that get slammed together and we're going to look for little polyglets when they come together. Doesn't work. Can't do a math on that. And contextual relationships. Well, here's that table expanded a little bit. You know, you can add maps. Divide, multiply. Raise one map to the power of another. You can do a bunch of advanced math. You can do calculus. You can do geometry. You can do all this stuff, but let's look at a couple of examples. Here comes the word. Derivative. That's a Forrester. Way back in the pre-Pleistocene, I had to take calculus. I have never used calculus. I intend never to use calculus. I'm as afraid of calculus as you are, but they rub my nose in this word called a derivative. It's an instantaneous rate of change in a function. Oh, God, that means an equation. Oh, I'm getting better. Okay. And the way you do it is you come up with the slope at that point to the line. So here comes the equation. This is y to the ex equation. And the tangent at that point, that's the slope, the derivative. And as I move down here, see how it flattens out? And I move up there, it gets steeper and steeper. That's what a derivative is. We have a derivative. It's been in front of you for a long, long time. Slope. We call it terrain slope. So if we've got not a curve, but we have this lumpy, bumpy elevation surface, and I'm not going to fit a line, but I'm going to fit a plane at each point. Each point is a square grid cell. I'm going to go there. I'm going to reach out and grab my 8 elevation neighbors, and if they're all the same, the slope is 0. If these guys are a little bigger and these are a little smaller, I'm getting slopier, 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 depending on how different they are. When I fit a plane to it. Direct analogy to your math professor. Well, that's the same as a tangent to a line, slope to a surface. And then I'm going to move around every one of those squares, do it again, do it again, do it again, and I'm going to record the slope. I have a slope map. Steep slopes, double black diamond. Flat slopes, man, you don't want alpine skis. Yeah, that works for terrain, but let's say that was a cost surface. First derivative is marginal cost as a map. So if you had any economics, microeconomics, we can take the concept of marginal cost equals marginal revenue, and that's when you do something. I have an MBA, and we studied that for months. We can do the same thing in space. It tells you when to harvest your tree for every quarter acre. Now, you're probably not going to go out with your harvester and harvest that way. But then we're going to move little windows around and say aggregate, such that it minimizes cutting in the wrong year, but I still stay within this harvest block boundary. There's a forester's interpretation. All right, that's all right for me, and I'm going to, all this stuff, remember, is written as columns, is written in the instructor notes, and in this case, several papers. So you can follow up if it makes any sense to you at all. Let's try another one. We're in mathematics. Let's try advanced grid math. If I have a slope map, And if I take the direction not the direction cosine, it's just the cosine of the slope angle, multiply it times the planimetric area, it'll tell me the slope area. See, you can plan a whole bunch more little rooty things on this slope. You can put more cattle on this slope than a flat one. So what do we do in GIS? Everything is planimetric. That's terrible. To move beyond that, you have to work with surfaces. All right, well, that would be an advanced grid map using cosines on a map. How disgusting. One more reasonably disgusting concept, and that's the calculus integral. The integral calculates the area under the curve for any section of a function. You go along. Come up with the area under the curve. Well, son of a gun, I can come up with the area, if you will, under a surface, but I'll add the third dimension I'll call volume. Direct movement from the concept in math that my grandfather studied into space, the integral. In this case, this silly little example, here's our elevation surface, is for these separate districts in the area. I just went in and said, what's the average, instead of totaling it up. What's the average elevation for each one of those? And then being honest, I also included the coefficient of variation. Maps are numbers? What's that coefficient of variation? Oh, this is terrible. It's a ratio of the standard deviation of the mean. But it says, how good is that average? Well, look at this green thing. Man, are there different elevations in there. Man, that's 39 as a coefficient. That says, that's a real crummy average. I would never make a decision with that. So what do you do in GIS? Is you assign the average to every county's polygon for the United States, kicks it out as a pretty colorful thing, and hand it and say, decision makers, go make great decisions. Well, if you don't include the coefficient of variation in that average, it isn't anywhere. Oh, but it's everywhere. And this is the map, and maps are perfect. They come down from the mountain, burning bushes behind. Data. You've got to represent this data if you're going to take us to the next level as a major technology. Well, that was so much fun. I want to try one more on you. How about distance? Miss Hall, second grade. Distance is the shortest straight line between 2 points. Shortest straight line, 2 points. Do you know anything in the world that moves by the shortest straight line between 2 points? In our Earth, light and laser doesn't move in a straight line. It gets bent by the atmosphere. Not much, but some. Nothing goes in a straight line. So every time you decide that that's the definition of distance, because that's what the Mayans thought it was, 3,000 years ago, you're going to make terrible decisions at nanohertz speed. That's scary. It used to be, this was hard. It would take them 2 or 3 weeks to come up with a few measurements. Couldn't screw up too badly. Now in nanohertz, you could do it for the entire state. Measure a whole bunch of distances between things. Wrong, but I'm done now. Miller time. Okay, shortest straight line between 2 points. But even a ruler is measuring distance with a grid. Because a ruler is just a cheap grid. It's just one row of a grid. Ticky 1, ticky 2, ticky 3, ticky 4. Those are really squares if you think about it. And what you do is you align the ruler between 2 points, and then you go 1 away, 2 away, 3 away, 4 away, 5 away, 6 away. You're really counting grid spaces. They're the little tickies, little tick marks. Or, over 2,000 years ago, Professor Pythagoras could say, oh no, keep your grid constant and count down, count over, square, sum, square root. B squared equals A squared plus B squared. Pythagorean theorem. Yeah, I can mathematically calculate it, and I don't have to twist my grid. Pretty nice. But let's try something different. Since Pythagoras, there ought to be another way to do this. And another way to do this is splash. By taking a rock, tossing it into a still pond. Splash. 1 away, 2 away, 3 away. As it ripples out, each ripple width is a cell, because we're moving in cells. So all of a sudden, I have a new concept of distance. Not shortest straight line between 2 points. I can relax 2 points. From here to everywhere, I have the concept of proximity. Fast as you can do 7 Pythagoras's the old way, I can cover that whole surface and tell you how far away everywhere is. And because I move out like waves, I can take into account different conditions. If you're going to drive your truck with a nice shiny paint job and you just polished it, you know, you're kind of constrained to the road network. Splash, and it's like a canal. The waves are constrained to the canal. 1 away, 2 away, 3 away, 4 away, 5 away, 6 away, until we come all the way out here and it says it's 26.5 minutes away because I've been measuring in minutes how fast you travel on the road. I relax the assumption, straight line. Couldn't do that except for about 3 decades ago. That is changing the mindset. And let's take it a little further. I've got ATVs in the back of that pickup, and I'm on emergency response. I can stop my pickup anywhere, and I could offload the ATVs, and I can start flying across the terrain. So now all of a sudden, it goes into the second part. It says, okay, leave the road on your ATVs. Now where can you go? And some places you can't go at all on your ATV. It'll tip over. You're going to have to walk. So this is a 3-step proximity function of movement. And the farthest away location in this little example is 96 minutes away. Otherwise, every 30 meters square, about a quarter mile, this is in Wyoming, I have an estimated time of arrival for the emergency team. And through plane geometry connectivity, I just ask the computer to go down that mountain of time as fast as it can. It retraces the route that got there the quickest. And in this case, it says that truck, to get to that hill, I've fallen and can't get up point, you drive 18 minutes along that orange in your truck. Then you get your ATVs and you drive for 14.8 minutes until you hit that kind of rose colored, so you go through that cyan looking stuff. Then you're going to have to jettison your ATV and you're going to have to hike for another 62 minutes. That's an emergency response system for back road country. Now, how powerful could that be? And you put seasons in there. Oh, I'm in Minnesota. It's winter. Boom, I just go right across the lake. That is changing how we think about maps. If we get out of the mindset that it's just a mapping technology. How about another one? I'm going to do that same splash technique, but I'm going to go splash at a location, and I'm going to say move out 1 away, 2 away, 3 away. But this time, know where my eyeball is. Am I on top of a 90-foot fire tower, or am I only 5 foot something or other down here? Now move out, take into account the elevation differences, and create rise over run. It's called a tangent. Splash. And it starts laying out the tangents all across the area. And if the tangent on the next ring isn't greater than the one before it, it can't be seen. It's a defilage. If it is greater, mark that location as seen. It's a view shed map. And that becomes a tangent to be on everybody else along that line of sight. Splash. I have a view shed map. Kind of like I stuck a lighthouse at your height and spun it. And the bright light hit that portion of the terrain. Anything that's not lit up, if you will, I can't see. Now see if you can fold that into something that you utilize in your primary discipline. Or how about this one? Well, don't just go to one location. Heavens, the computer's there to compute. Who cares? Where this one will take 3 nanoseconds, this might take 5 nanoseconds to compute. What do we care? So what I had the computer do here is to go to every road location, treat each little cell like it was a fly's eye, flash, mark everywhere you can see. Go down the road a little bit, splash, everywhere you can see gets marked with a 1, but 1 plus 1 says I've been seen twice by the road. This is a visual exposure density surface. Where you see the red, the warmer tones, lots of the highway sees that. Ha! Billboard space! For surface. I don't think I'm going to clear cut there. I'm going to go over right there and I'm going to rake the forest and no one will ever know the difference. In fact, I could probably move into a lot of those greens because they're all coming from California and they're sipping their lattes and they're chatting the whole way. They're probably on autopilot. They're not even looking. So if you're not seeing too often, maybe I could still rake the woods there. Or, this is what math was 1,000 years ago. They'd say, whoa, what next? Well, the what next is a weighted visual exposure density surface. Why, this is an interstate. It has a lot more traffic. Those little eyeballs, those little square eyeballs, making a composite eye like fly's eye, are more important. So when they look out, they stomp a bigger importance down. And look how it kind of shifted it. This was really, really tough stuff. This was the worst when every road was considered the same. Now there's the worst. Went from viewshed map, binary, I can see it. No, I can't see it. Visual exposure density surface. How many times do you see it? Just count it. Weighted visual exposure. Sum the weights. Well, that's math. We're cooking along here. What about an analytic tool? This is spatial statistics. Now we're going to look at the numerical relationships. I can hear the mind blocks falling. Well, there's a bunch of things that statisticians recognize. Min, max, median, mode, all those kinds of things. Joint coincidence, statistical test, a t-test, a chi-square test. Well, the contention is, why do all those things with maps? Why can I do them with maps? Because they're an organized set of numbers in continuous space. I can't if they're a collection of irregular spatial objects. I can't do math or stat on them. Well, let's do the same thing. There's predictive. I can talk about regression. I can do data mining. We do that quite a lot in geobusiness. I can do clustering, maximum likelihood, things that the statistician recognizes. So let's start. Let's say I've got some measurements in space. I went out in the field. I'm a biology student, let's say. Let's say I'm a geology student. Let's say I'm a soil scientist. I could be any kind of an ologist. They collect field data. And what do they do when they come back? In this case, divide by 16 and talk about the average. That is assumed in geographic space to be everywhere. Standard deviation is 26.2. It's bigger than the mean. That says there's only one rule in statistics, and that's about it. If your standard deviation is bigger than the average, don't use that average to make a decision because you're really going to screw it up. That average isn't typical. Hell, it's bigger. So what are we going to do? Sounds like Ghostbusters. What are we going to do? Well, let's see if we can explain some of that variance in geographic space. So same numbers, however I collected in the field the latitude and longitude. I had a little GPS unit with me when I went out there. So now I'm just plotting on the z-axis is parts per million of lead, let's say, in the soil. Wow, pretty dirty stuff up here. Oh, not bad down here. So I'm now viewing the spatial variance in the data. And now I'm just going to run a little window around there, and I'm going to interpolate it into a continuous surface based upon what's around it. I filled in the holes. Kind of like I put modeling clay down on those spikes and just smoothed it off with a knife. I now have a spatial distribution, math stat speak, and a numeric distribution. The numeric distribution. Fit Gaussian or standard normal curve to the data. Here I fit surface. Direct analogy. And if I put the two together, there's your mean. It's this little thin line. And it does exactly what it's supposed to do. Half of the volume is above it, half the volume is below it. It is hardly anywhere, and you're going to screw up if you use it as a decision. If I take statistics, just descriptive statistics a little further, and I calculate the standard deviation, this line right there, that red line, is mean plus the standard deviation, the tail of the distribution in stat speak that says anything that's inside that line is unusually high. You wouldn't expect it. You've got a problem. Dead children, maybe. This was lead in the soil. I'd have some lead abatement. I don't have to do it down here. They don't have any trouble. And that's kind of what this is saying, is when you threw out, and most GISers, all scientists to date, I'm not going to say all, but most scientists to date, throw out all that information about spatial relationships and patterns. Here, both of the two areas came in under the requirement to be a Superfund site. But now when we put them two together this way, see that little red area? Both of those are out of compliance. Put them together and you got a big area to manage. But you wouldn't have picked up using non-spatial statistics. We use spatial statistics. Why? Because we've confused the hell out of them. Next one. Last of your little statistics slide. Here's my elevation. There's my slope. Let me try clustering. What cluster does is it goes to every location and says, what's your elevation? What's your slope? And in this weird two-dimensional space, it says, here's increasing elevation, here's increasing slope. Every one of those points fall on one of those points, one of those locations. Using standard clustering techniques that have been around since the 30s, I just asked it to group them. Those that are most similar, they're kind of high, are on this side of that red line. And those that are most similar, low, are on this side of that line. And I just divided your project area into two statistically distinct groups. I said 3 clusters, it would have put it into 3. Clustering. Been around for almost 100 years. Non-spatial. The social sciences use clustering all the time to analyze the answers on the spreadsheet. You know, they have a high, and those are the fruitcakes, and the low answers to that question. One's a rip wings off butterflies. I don't know, whatever it was, they put them into groups. Best Buy, I worked with them a lot as one of the clients. They come out with names as to how you shop. Bruce buys differently, and Rachel. Based on, this is called data mining. But most of our data mining is non-spatial. The contention here is we really think maps are a collection of numbers. There's a spatial data mining. Let's try this other one, predictive statistics. So here's the elevation, slope, and I'm going to say, what's the correlation between those two things? Well, this is the God-for-all equation to calculate correlation. It has a whole bunch of sums of this, but each xy is just sphere like this guy did, a number. And then you pour it in this big hopper, and then it comes out and says, well, those two are correlated, 0.432. Positive, so it says when one gets bigger, the other one gets bigger, kind of. One would say when one gets bigger, the other one gets just as big. They move in lockstep. Negative would say when one gets bigger, the other one goes down. Huh. Well, they're kind of correlated. Write your papers for Scientific American. No! You got an equation. You got all this data. Let's put a little window around there, and I'm going to calculate the correlation within that window, and I'm going to move that window all over. So now instead of one number summarizing 2 different years on my plot or something like that, are they correlated? Now I have a map of correlation, and when you see that go green, it means those two things are actually negatively correlated there. Right there is that 4.32, and up here it's 100%. Perfectly correlated. There goes the baby and the bathwater. If you take data and just color it, keep that in mind. Haunt. I hope that haunts you the next time that you're out thematic mapping. That just haunts you in the shower. You keep checking behind the shower curtain to see if there's a bloody knife or anything. Think of that. You're really setting up the decision makers to make terrible decisions at nanohertz speed. All right? Yep, got it right there. We got a couple of little ends to tie up. But what's that other one? The other one, if that was the mathematical framework, that's the one I just wanted to beat you on the forehead. Get you thinking that way. This other one says, well, what about data structure? What's the future influences in data structure? Well, we started out with latitude and longitude. Yeah, that's been around for a while. Kept us from sailing over to the sirens and the serpents and all that. So we did pretty well. Now that's at 30-degree grid lines across the Earth. There are 9-degree grid lines. And here I've planimetrically projected it and put the grid over it. That is 2.5 degrees. Now, that sets up what we'll call an analysis frame. And I could keep data for every one of those little squares. Put a number in there. Put a number in there for population in that square. Then on another data layer, and think of it maybe as another spreadsheet tab, I'd have another layer for this matrix that might tell me what religion's there. I might have another one that will tell me what vegetation's there, what's the average temperature. I could have all these stacked up layers that have exactly the same framework, data structure framework. The computer just goes, oh, I love it when you do that to me. I love it. It's all organized. There's no topological structure I have to unweave. There's no pulling in polygon, line crossing, other, none of that crud. I just go to a square, and like it was a shish kebab, I just go, pull up the numbers, and what do you want me to do to them? All of the spatial topology in a grid-based system is implicit in the grid. You don't have to store crud. That's what the computer needs to do mathematics. It needs to be consistent. All right? So here it looks like a spreadsheet. This literally is. I pulled numbers out of there and I put them into that spreadsheet. Now, you probably won't work with this one. Each one of these is about 140 miles by 140 miles. And some of you are saying, well, that's not true down here. We're going to talk about that a little later on. But certainly at the equator, exactly 140 by 140. And that's 18,000 square miles. That's probably not an average spatial parcel you want to work with, but it sets up the concept. Cell locates in space that's consistent in each one of the grid data layers in this map stack, it's called. Value that sits in that matrix tells you the information. What is the population? Now let's look at it slightly differently. Here's my little spatial database, or my spreadsheet concept. Here's that Wyoming landscape. 30 meters squares, about 100 by 100. The way that we store this, if you're going to do this kind of mathematics, is we store it in a table. And tables are lexicographic, starts out at the top, row, next row, all the columns along the next row, the next row, the next row, turns into a great big long string of numbers. So in this field called elevation, just by the ordering of the numbers determines where I am in that analytic framework, analysis frame. So it's an interlaced relational database management format. Data field is the map, and then all the values, records down there, contain all the information on all the maps that are in the layer. Very efficient way to store it. Not the way you store it if you came at it from a mapping point of view. Like Esri stores their grid data, separate file for every map. Because they're mappers. Once we've done that, we have the latitude and longitude for each one of those squares. So we stamp the latitude and longitude in there, the centroid of that square. What's its latitude and longitude? And now we have a universal spatial key. If you do it for the data you collect in space, you have latitude and longitude, or you can do it after the fact by slamming this grid down. But the important thing is that once you have that matrix of numbers and its latitude and longitude, you can take any map from anywhere, reshape them, and jam them together into analysis. All of a sudden, the sociologist's information can be mixed with the hydrologist's information if you wanted to, because of what's called a universal database key. In this case, spatial, and its latitude and longitude. Mega technology? Deep stuff. Last one on this one, and then we hit the next final. Okay, so we have what? Those are numbers. Where? Or in the cells in the matrix. Let's see how we do this. The user comes in, drags a study area, maybe in Google Earth. As soon as they have that study area, that's your geographic extent, the next thing it does is say, what cell size do you want to analyze? Well, it's really detailed. I want to analyze at 30 meters. Oh, heck, this is a broad regional thing I'm working on. Let's make it a half-mile size square. It's you tell it the spatial resolution. And you just put one in. 30 meters, 100 meters, 1 kilometer. It's what you think is appropriate for analyzing for your project. It then automatically, thank God, determines where every little square is. Number of rows, number of colors. Figures it out. Automatic. All those cutoffs, it builds your analysis frame. Then you turn on the database. For every one of those records that were spatially aware, they just get poured like a faucet into the cells. Now I have continuous map variables with one caveat. Because often you'll have more than one value fall on a square. And sometimes you won't have any fall on a square. So you got to massage it. shish kebab of numbers. And let's say there's a whole bunch of numbers that fill in the same square. You could average them. You take the biggest, take the smallest, your choice. You just tell the computer. Then I have a map layer, a variable. All right, for those that are GIS centric, yeah, but this is latitude and longitude. And we all know those silly things come together at the top, and it's no longer a square, it's this weird trapezoidal thing. Doesn't work very well. So if you're analyzing the polar areas, this probably isn't the way to do it. But they're most of the Earth. They're pretty square, particularly when you bring them down to 30-meter squares. They're really square-like. All right? Last thought. With a little bit of history. Start out in the 70s. We knew what this technology was. We had to automate the drafting process. It was automated cartography. Could we get that computer to draw a map? Several years of labor and fighting with decks of cards through glass windows to $3 million cyber system over here. Supercomputer. Yeah, you could finally draw a map. Well, I could have drawn that in a day. It took you 6 months. But eventually, it kind of worked out. Particularly, the Hayman fire. I think I might have to change that vegetation map. Before Hayman fire, after. Well, now that's really valuable to have automated cartography. Okay, so we did that. 70s. Then in the 80s, we said, whoa. If you can keep track of parcels in space, we can keep track of information about those parcels. Think of timber stands. What kind of tree is there? How old are they? How big are they? All that kind of stuff. What kind of soil is it on? So we have this where, you're keeping track. X, Y, thud. My polygon of timber stand number 57. Then I'll walk over this linked table. An ID number, and I'll see what's going on inside that timber stand. So that was the rage in the 1980s. My God, you can link a database. So instead of this is fun about ArcInfo, the info side of ArcInfo was a database developed for the DG computer for banks. Jack went out. It was the only database that he could fit in, and it was a DG requirement by BLM. So he grabbed the only database he could, designed for keeping track of customers by ID numbers. Well, the ID numbers just became polygons and lines and points. Okay, we did that. We linked our non-spatial information with our spatial information, primarily for query. Then we tinkered around, and we went into this map analysis stuff, the 90s. All in place. Actually, most of that has been in place since the late 70s. It's not used. Why? Because the user community has no idea that it could use and could come up with predictive statistics and stuff. No, it's just been sitting there, kind of idling. And that's where we went into the 2000s. The 2000s was this confluence, this perfect storm of internet, GPS, principally, and personal computers, I'll say. All of a sudden, on your very own data, desktop, you could have these maps, you could pull them down off the internet, you could link them in with GPS, drive, and do all sorts of nifty stuff. So we kind of just went out and did a whole bunch of more mapping. See what's happening down here? We started out mapping, then we went to data structure, then we went to analysis, and then in 2000 to 2010, we were pretty much back to mapping, geo-web mapping. And we were linking it to mobile devices. Well, I'll contend that where we're playing now on the frontier is that, the data structure. And then, it's going to be analytics again, because we're going to change our data structure. So let's see what I mean by that. Right now, for our grids, thanks to Descartes, we work with squares, which don't fit a round globe for beans, but that's where we work. So I think we're going to take our squares, and we're going to represent them as hexagons, like a beehive. And there's a real good reason why we're going to do that. Is to go from the center of this location over to here is a different distance from the center to there. Notice that makes things inaccurate, that screws up, makes complex algorithms to solve and all that. See this guy? Here I'm at the center. And to go to any one of my neighboring parcels is exactly the same distance. Called a robust mathematical structure. And that's going to really make things more accurate, faster, and we can do more things. And what's really staring us in the face, 3D space. Matt was right. But to take cells to 3D, we got that same problem. It's goofy. Because there's orthogonal movements, diagonal movements, weird movements. It just isn't. So then we use pentagonal dodecahedral. It has 12 sides. It means in three-dimensional space, it's the same distance to each one of those, and they nest just like the beehive nests, but in three-dimensional space. Now all of a sudden we can do very complex flows and cycle modeling in 3D space. That's coming at you. And if we can do very complex flows and cycle modeling in 3D space, plus all of our traditional stuff is going to be a lot more accurate. I think we're going to revisit analytics. Last one. Yep. Ooh, last one. Education. Okay, it's been a technical tool since the 2000s. The big thing. And this analytical tool will kind of fell off to the wayside. Even though we did in the 90s, we got all excited, we started building models, but then it was lust. It was, I want that map to show up on my Surface tablet. And this is kind of what's happening to our community. Started out when I did in the early 70s. There were about 40 people that worked on this. We used to hold at Harvard a conference. When we assembled for the International Conference in Spatial Analysis, 40 people could get enough money to come. All 40 were very versed in math and stat. In the 80s, there were several thousand pace setters that started grabbing this stuff and taking it out. And then in the 90s, there were hundreds of thousands, mainly because GPS arrived. And now, billions. And every one of those billion users, because I can access Google Earth, I am a GISer. I know everything I need to know about GIS. Google Earth. We're done. And that's what's been killing us, because what moves us is the marketplace. The marketplace now has little consciousness. And if you're going to make money, you do what the client wants. You don't show them something new. You do just what the client. So we're being dragged forward into the future at this moment by the lowest common denominator, which doesn't really understand what math would be. So that's what I'm interested in turning around. There's matching numbers first, why so what. And these are the final 3 slides. ISTs and the ologists. We have been dominated by the ISTs, the technology experts. The GIS special IST, for example. The mensuration IST, forestry. The ISTs are technical. The ologists are domain experts, hydrologists, the ecologists. And what we're working on is merging the ologists who use science with the ists that use technology to come up with solutions. GIS expertise principally is where's what. Spatial reasoning that the ologists need is why, so what, and what if. But it goes beyond that. Decision makers. They have to understand this technology enough so they don't go, voodoo, get that out of here, non-admissible. Oh God, then we have stakeholders. Oh, I know what that answer should have been, by God. So we got to deal with them somehow. Policy makers. Whoa, this would be good for society. And the public, oh, I don't know anything about this, but I'll vote yes or no. So that, it has to go beyond just training GIS specialists. It has to be in other courses. And that says GIS expertise. I think we are trivializing our applications. Oh, I could use it to find the nearest pizza. And to spatial reasoning. At the same time, we're complicating it. Conclusion and upshot. Tomorrow's arena will be radically different than the past 4 decades, and there they are. Computer mapping, spatial database management, map analysis and GIS modeling, GeoWeb and mobile devices. It'll be radically different. In the future, geotechnology will exploit the numerical characters. Scientific use of data. By extending the scientific use of data, we've got to get the scientists to use this stuff. We're going to really change society and get better decisions. Spatial solutions to devices. This is a revolution. The idea that a machine can see a map and understand a map as well as you can. Got to be digital. Has to be explained in digital terms because machines work in digital. The idea that we're now interfacing spatial information with machines, robotics, and then spatial reasoning and dialogue. Maybe that's how we can capture some of those public stakeholders and all that, is by using this as a communication tool. Communicate better. Particularly the what if scenarios. Well, what if this? This is what it would look like. What if this? This is what it would look like. These are the summary economics. These are the differences. Quantitative map analysis and modeling completely changes our perspective of what a map is and isn't. Where do you go from here? First step, you take that handout and go and take a look at the slide set. Remember, it has instructor notes. And then if you go to this innovativegis.com, there's all those books. There's 1,000 pages to play around with. And they're organized into 4 books. All right, went beyond my time. I got excited, I'm sorry. Jeez. But any burning questions, and you can leave during the burning questions. Because you probably have burning beer thirst or something.
So how do you propose altering GIS certificate programs to include more statistics and math?
I'm not going to change the certificate. I'm going to recognize that there's istanologists. If someone who chooses to be an ist, we got to have somebody get that data right. But the ologist says, I need this stuff in my course. So somehow the teachers have to treat the teachers. In other words, there ought to be teacher workshops that says, in social science, this is how this could extend your understanding. It's got to be tailored to the ologists in their courses.
So yeah, so you would include a GIS within biology or mathematics. Or...
But actually in that course, not GIS for biologists.
No.
What my fear is, and I've seen that happen, is it ends up 3 weeks on what's a projection. And, I mean, you try to make them specialists for far too long. And that's another positive thing is grid data is pretty darn easy. It's just where with a bunch of numbers in it. Most scientists are pretty comfortable with a bunch of numbers organized. So I think you can talk to them real quickly. And you don't have to tell them what's the difference between a Mercator and Lambert projection and all that stuff. That's for the IST to take care of and the software. Any other thoughts? Yes?
What kind of initiatives would you maybe suggest for merging GIS into the STEM? I mean, that's a big thing right now.
Well, what's happening with STEM right now is they're kind of looking at the T in STEM, science, technology, engineering, and math. And most of the curriculum that I've seen is showing them how this technological tool could be used, not an analytic tool. So that's, I do it at the college level. You know, some sharp high school kids might be pretty good. But in order to do the analytics side, you really have to have some foundation, really pretty minimal in stat and math. Understand it as a mathematics. So it'd be at the college level. And it would be curricula within a domain discipline. Just like statistics started out. I did. I had to take my courses in statistics, and now all of a sudden there's business statistics, there's natural resource statistics, there's statistics for social scientists. See how they translated it into the domain experts' language. That's what we need to do.
I was thinking about the sort of, the wall-to-wall coverage of, grids for the whole world. And it's a great idea, and I mean, it's, of course, it looks awesome, but I'm wondering how to get there if, stuff like, I mean, we're only going to get that data really from like remote sensing, or maybe not only, but mostly, right? And so how are we going to do that if, like, we barely had the political will to get up Landsat 8? How do I'm thinking about that sort of the public and the policy makers. And how like, what are your thoughts? How is that going to happen?
I think there's two ways. Remote sensing, remember, that's my passion. That's what I was trained in. I like it because it's already set up just right. So we're going to get more and more from remote sensing. But that only describes the physics of light interaction at that square. And, not everything's in that physics. You don't know who lives there would buy your product or not. The light doesn't tell you that. So it's only going to take us so far. Then what we do in geobusiness is we do address matching. If you swipe your card, I know where you live, I know where you work, I know all sorts of stuff about you, and I know what you bought, and I know how much you bought, and I know all this kind of stuff. So we just take, when you swipe your card, if we want to target market you at home, we just assign through address matching. It goes from your address to latitude and longitude, and it gets tagged into the record. So that's another way to do it. If you're a scientist or agriculturist who wandering around a field, it just says every time that you have your little field data logger, you push the button that says stamp it with the. I took a soil sample right here as a soil sample ID, the one that we use. You push the button and out comes this little label that wraps around the bag that you put the dirt in, that you put the soil in. And it goes off the soil lab, so when it comes back, I know where those came from, and I can interpolate them in a nutrient map for the field. So I think it's going to be the data loggers in the field. I think it's going to be address matching for all those things that aren't logging directly in the field. And then remote sensing. So it's way different than the map down we had in the 90s. What we had in the 90s were thousands and thousands of drawers and hundreds of whole file cabinets of paper maps. And we literally, for 10 years, we brought out those paper maps. We took a thing called a digitizer and we dragged it over every line that was there. That was a pain. I think this transition, because of GPS, is really going to be easier. You survived. 15 minutes late. Okay, well, I hope you come back, because the next one we're going to look at natural resources in ag and how they're dissimilar yet similar in their applications using